All right, hello geometry. Today we are continuing with circles. We are going to do our last lesson over measurements of circles, kind of involving angles and chords and lines like that. All right, so starting off with this warm up, given O is the center of the circle, determine everything we can about this diagram. Well, given that O is the center of our circle, we have a couple lines. We have CB cutting across as one chord. We have AD cutting across as another chord intersecting at point E. None of them actually pass through our center O. But what we can determine is that we have some vertical angles right here. We know those angles that are across an intersection are vertical. Another thing I can determine is I look CDE, this inscribed angle, and CBA both inscribe the exact same arc. They both inscribe CA. So that means both those angles, because they intercept the same arc, would have to be equivalent as well. I'll put 2 dashes to show they're different. And then similarly, we see that DCB inscribes DB, and DAB also inscribes DB. So these angles would also be the same because they're both inscribed angles that intercept the same arc. So pretty much that's about everything we can figure out. We can't necessarily figure out what any of the values are, but we know that angle DEC is congruent to angle BEA because those were our vertical. We saw that angle CDA, was congruent to angle, let's see, that was CDA. That was the same as angle CBA. And those were our inscribed angles. And then for the same reason, we saw the angle, where are my angles? Angle DCB is congruent to angle DAB. Once again, from being inscribed angles that intercept the same arc. So given this information, we can actually determine that triangle ABE and triangle ACD or CDE are congruent, or not necessarily congruent, I apologize. They're similar because we have angle similarity. We know that if we have at least two angles that are the same, similarity. I spelled that wrong, but I don't care. We know that if we have at least two angles that are the same, we can prove that they're congruent. So for example, we have our vertical angles and we have our red inscribed angles or our green inscribed angles. So we know that all the angles in the triangle are the same, so they have to be similar to each other. That was our way we proved triangles were similar. So using that information, knowing that relationship, could we solve for x given in this shape? Well, I know my two triangles are similar to each other, so I know that my sides would have to be proportional because I know that works for every similar shape. So I know the ratio of my sides are going to be the same. So 8 over x could be one ratio, and this is going to be equivalent to 6 over 3 as my other ratio. And once again, once I get from here, I can always cross multiply. 8 times 3, x times 6. Well, that gives me 6x. 8 times 3 is 24. And then I can just divide by 6 to let me solve for x. And I get x equals 4. So what we can determine from this, if I have two chords that intersect at some point in my circle that's not the center, if I just have two random chords that intersect at some point that's not the center, I know if I were to form triangles out of those chords, my triangles would be similar to each other. Therefore, my lines would have to be proportional. My shorts would match with my short lines, and my long lines would match with my long lines. They're not necessarily going to be the same length, but they're going to be proportional. So for example, in this triangle, we could say, or in this example, we could say AC times AD, our long times our short, would be equivalent to BA times BE, or sorry, AE. So as long as we can match those longs together, or shorts together, or short times long and long times short, we should be able to solve these for x. So you're essentially just taking the same pieces from the same line and multiplying them together. So for this example, we have x times 8 and 4 times 6 as our two pieces. Long times short, so 8 times x, and then long times short, 6 times 4. And all I have to do is solve this. So 8 times x is just 8x. 6 times 4 is 24. I can divide by 8. And I get x equaling 3. Super simple, super easy, just some quick multiplication and division. Same idea with the second one. I see I have 2 times x, long times short, and then 6 times 3, long times short. So 2 times x is just 2x, 6 times 3 is 18. So I have 2x equals 18, divided by 2, and I get x equals 9. So once again, these problems are super simple. All we have to take is one piece times the other piece, and then we're good to go. Sometimes we can add a little bit of depth to them if we throw in an expression. So for example, I have 4 and x times 5 and 2 times 6. 2 times 6 is going to stay the same, but 4 times x minus 5, I need to make sure that x minus 5, that whole expression is in parentheses, because that whole expression is being multiplied by my other length. So that means when I'm simplifying this, 2 times 6 is just going to be 12. That's easy. But 4 times x minus 5, I need to distribute that 4 into my problem. So that's going to be 4 times x, and then 4 times negative 5, which is negative 20. And then from here, this is a simple two-step equation we can solve. Inverse my constant to get 32 equals 4x, and then inverse my coefficient to get x equals 8. Easy enough. And once again, if we want to check this, I could plug 8 back in, and this would be 8 minus 5 is 3, so does 4 times 3, that equals 12. That's the same as 6 times 2, which equals 12. So we know they're the same, they're proportional. Same idea with the second one. We just have more harder expressions. They just gave us more expressions. So we have short times long is x plus 4 times x plus 1 equals short times long, which is x times x plus 6. Now with this one, we're going to have to think back to Algebra 1 a bit. Actually, a lot of today's lesson is going to be reflecting back in Algebra 1, because we're going to have to FOIL. We're going to have to double distribute. We're going to have to take x times 1, which is x squared, plus 1x, 4 times x, which is 4x, and then 4 times 1. It's multiplying polynomials, thinking back to Algebra 1. We can simplify this to x squared plus 5x plus 4. And then same idea for this one. X times x is x squared. X times 6 is 6x. So we got a lot of things going on here. We have x squared plus 5x plus 4 equals x squared plus 6x. So thinking back to Algebra 1, one of the ways that we could solve this is let's start combining our like terms. Let's get these like terms together. So I'm going to get all my x squareds together. So if I inverse my x squared on this side, I'm going to have to inverse it on this side. So, well, if I subtract x squared from both sides, they both have 1x squared, so that's actually going to cancel that out. So that'll leave me with just 5x plus 4 equals 6x. And this I can easily solve by just inversing my 5x, inversing 5x, and I get x equals 4. We've actually solved that. We didn't have to worry about anything with quadratics yet today. But we could have solved that if we needed to. So x equals 4. All right, so that is if I have two chords that intersect across my angle or across my circle, how can I solve them? We just know it's short times long times short, or short times long. Set those equal to each other. That's super easy. Now, if I have lines that intersect from outside my my circle, this is going to be very similar to the side splitter theorem that we did in trigonometry, or a side splitter theorem we did with right triangles. Our side splitter theorem, if we had a triangle that had like parallel lines that cut across it, and we created similar triangles, we could see that it was like the short end times the entire length would equal the short end times the entire length, where essentially we have this small similar triangle and we have this large similar triangle. So what we can do with circles in order to help us solve that is essentially we have this little theorem, our segments of secants theorem. It's going to be my short side times the entire length equals my short side times the entire length. Those are going to be our two values. So EF times EC equals EF times, or EG times ED. So let's see some examples though. It's short times long, or short times full, short times full. So my short side is 9 times my entire side of this line is, my entire secant line is going to be 20. My short side is 10 times the entire secant line. If we look, this side is x here. So 10 plus x is going to be, just, I can write that as 10 plus x. It's going to be the expression, my x length plus 10, or 10 plus x. Now this I need to solve. So the 9 times 20 is pretty easy. That's just going to be 180. But this 10 plus x times 10, I have to distribute that 10 into my problem. So that's going to be 100 plus 10x. Well, this I can solve. It's just a two-step algebraic expression, or algebraic equation. I inverse my 100. 180 minus 100 gives us just 80 left over, which equals 10x. Divide by 10, divide by 10, and we get x equaling 8, if my pen will write. Once again, we could check this by plugging 8 back into the function. If I plug this back in, does 9 times 20 equal 10 times 18? 10 times 18 is just 180. We know that's the same as 9 times 20. So we know we did it right. We know we solved. Same idea for the second question. It's my short outside times the entire length, which the entire length of this line is going to be 15. And then that's going to be equal to the short outside of 5 times the entire length of this line, which is going to be x plus 5. It's my variable plus my constant. Once again, I'm going to solve this the exact same way. 6 times 15 is 90. 5 times x is 5x. 5 times 5 is 25. And once again, we're down to a two-step algebraic equation. Inverse my constant to get 65 equals 5x, and then inverse my coefficient to get x equaling 13. Once again, if you want to plug it back in to check, this should work out. All right, let's look at this one. I said we wouldn't have to worry about quadratics yet. This one we might have to think a little bit extra. We notice our x is on the outside of the secant lines, or on the outside of our circle. That's going to make it just slightly harder. We'll see why. So we know it's outside times entire length, outside times entire length. So if I start off my equation, I have 5 times the entire length of this line, which is going to be 12. So 5 times 12 will be equal to my outside, which is x, times the entire length of my line, which is x plus 4. So we actually had x show up twice in this problem, which is going to make it a little bit harder. We're actually going to think quite a bit on this one. 5 times 12 is 60. Easy enough. X times x plus 4. Well, I know I just need to distribute. Let's get that pen up there. Come on, there we go. All right, so x times x is x squared. X times 4 is 4x. All right, well, looking at this, none of these are like terms. So actually thinking this, we're going to have to think all the way back to Algebra 1 and think, okay, how do I solve quadratics? Because if we look at it, this is the quadratic equation that we need to solve. So the easiest way we solve quadratics, the first method we always had to do was we had to get everything to one side of our equation, thinking back to Algebra 1. So first thing I need to get is I need to get this side equal to 0. So I'm going to inverse 60. None of these are like terms, so none of them are actually going to be subtracted by 60. So this is going to be equal to 0 equals x squared plus 4x minus 60. Now, thinking through how to solve quadratics, one of the methods we used last year was the quadratic formula. That's your opposite of b plus or minus square root b squared minus 4ac all over 2a. That you probably didn't think you would have to hear me sing again. The other method we solved was factoring. Now, factoring was that box and diamond method. So we created our little x, we created our box, and this would allow us to help factor our equation into two easier pieces that we could solve. What we had in the numerator, we always took the first term times the last term. So negative 60 times x squared is negative 60x squared. And then in the bottom part of our x, we had our middle term, our 4x. So we had to think what two numbers multiply to get negative 60 and add to get 4. What numbers multiply to get negative 60, add to get 4? Well, two numbers that can multiply to get negative 60 and add to get 4, we can do negative 6 and positive 10. We put an x with both those. Negative 6x and positive 10x multiply to get negative 60x, and negative 6x and positive 10 multiply or add to get 4x. So that works out. So we're going to split the middle term into negative 6x and positive 10x. And so how our box worked out is we could put an x squared, and we put our x squared in our top left. We put negative 60 in our bottom right. And then I would put negative 6x in one of my boxes and 10x in the other. And from here, I had to write numbers on the outside that multiplied in to create our box. So what two numbers multiply to create x squared? Well, that's x and x. X times what number creates 10? 10x? Well, it's going to be 10. X times what number creates negative 6x? Negative 6. And does negative 6 times 10 create negative 60? Yes. So I know my two factors of my problem are x minus 6 and x plus 10. So we just factored our quadratic. Now, the reason we wanted to factor our quadratic, the reason we could do this is we could easily find what the two solutions were. It was just the opposite of my numbers that showed up. So x would equal 6 and x would equal negative 10. Those were my two solutions. Now, okay, thinking about this problem, I got two answers. How is it possible that I got two answers for this solution? Well, if I look at my two answers, I got 6 and negative 10 as my two solutions to my quadratic. Now, looking at my problem, thinking back to geometry, which of these makes more sense? Is this line right here, is this going to be 6 long, or is it going to be negative 10 long? Is it possible for a length to be a negative? Negative 10 is not actually going to be any correct solution. So the only correct plausible answer is going to be 6. So it's 6 times 4, or 6 is going to be our x. Now, once again, we can check that. We can think, okay, if this is 6, this whole length would be 10. So it'd be 60. We know that's already 5 times 12 is 60. So we know we have the correct answer. And we are good to go. All right, moving on. We have one last thing to talk about. And this is actually very similar. So sometimes we have a secant line that's equal, or we have a secant line that touches a tangent line. So once again, a secant line passes through my circle. A tangent line touches my circle at only one spot. And we can actually calculate these the exact same way. So we know it's the outside times the entire length equals the outside times the entire length. That's what we were doing with our secant lines in those last problems. Well, if I look at this, I still have outside times the entire length. The outside of this line is just EC. The entire length of this line is also EC. So if I'm calculating this, it would just be the outside times the entire length is the same thing. So EC would be squared. So it's going to be essentially, another way to think about this is the outside times the entire length is still normal for your secant line. For your tangent line, you're just taking that value and you're just squaring it because you're multiplying itself by itself again, and that's just going to square it. So we can easily use that to help us solve. My tangent line is squared, and then it's outside times the entire length. So my tangent line is x, so it's just going to be x squared. I'm just squaring that value. My outside times entire length, my outside is 9. The entire length of this line is 16. So it's 9 times 16 equals x squared. Well, x squared is just going to stay the same. 9 times 16, if we multiply that together, it should give us 144. So all I have to do in order to get x is take the square root, because we know that inverse square root is the inverse of a square. So if I square root 144, I'm left with just 12. So 12 is going to be my answer for x. Same idea with this one. I know it's my tangent line is squared, so in this case it's x squared again, equals outside times the entire length. My outside is 4. The entire length of this line is going to be 16. 4 times 16, I believe, is 56. So we get 56 equals x squared. And this one, we're not actually going to get a nice, easy number like we did with 12, because if we take the square root, we have to figure out what's the square root of 56. And it's not going to give us a nice, easy number. But I have it written down here. The square root of 56 should give us 7.48 if we round to 2 decimal places. The 7.48 is going to be our solution. Once again, you can plug that back in. We could do 7.48 squared. Does that equal 4 times 16? It should. It should work out. All right, last question. Last question where we're ending it out. This time, my x is on the inside of my circle. Let's see, does that make any difference? Well, I know it's my tangent line squared, so this is going to be 24 squared is going to equal my outside of 12 times the entire length of my line. Now, once again, the entire length of this line is x and 12, so it's going to be x plus 12, where I'm combining them together. So I have a little bit more algebra to do on this one. 24 squared, I can just plug that into my calculator. That should give me 576. And then I can distribute my 12 in order to simplify this side. So 12 times x is 12x. 12 times 12 is 144. Oh, and here we go. Another two-step simple algebraic expression. Inverse my constant, which 176 minus 144 should give me 432. And then that equals 12x. And then just inverse my coefficient of dividing by 12. And x equals 36 in this problem. Once again, if I really wanted to check, I could plug 36 back in to see if it works. It should, in the long run, check out. So we have a lot of different strategies to solve. Once again, just sort of doing a quick reflection back. If we have chords that cross our line, if they're just chords that are all on the inside of our circle, chords on the inside of our circle, all it is short times long equals short times long. Short times long equals short times long. Easy enough. If we have secant lines where they're on the outside of our circle, what we had to do was it was the outside times the entire length equals the outside times the entire length. Easy enough. And then technically it was the same idea for our last tangent line and secant line. It was outside times the entire length equals outside times the entire length, but it's the same, so we just really just squared that value, multiplied it by itself. That's where we're going to end it for today. Let me know if you have any questions. We're going to practice over this. This should be our last lesson we learned before our assessment over angles and chords and secant lines involved in our circle. Once again, let me know if you have any questions. Have a great rest of your day.